Hi guys, welcome to our fourth video in chapter 17. This video is going to cover chapter 17.4, which is all about instantaneous rates and reaction mechanisms. Okay, so to jump right into it, an instantaneous rate of reaction is the rate of consumption or of production at a specific time. Okay, so this is wondering if I'm looking at this graph of concentration of my hydrogen peroxide over time, I'm wondering what is my rate of reaction at 3.5 minutes, right? I'd like to know that. Now, we can find that by determining the slope of the straight line that is tangent to the curve from a concentration graph, right? So this, if I look at what this is, right? Tangential means that it is touching the curve but not crossing it. And if I calculate my rise over run, my delta, my change in concentration of my hydroperoxide over my change in time, I can calculate a slope, and my instantaneous rate would be the change in hydroperoxide over the change in time. Okay, so that's the instantaneous rate of reaction. Now, I want us to get into a little bit more of a specific breakdown of how reactions work, right? And that is the mechanism reaction, or reaction mechanisms. So, a little brief blurb on how reactions work, right? We have things called elementary reactions, and they are just like they sound. They are simple. This is a reaction that occurs in one step, and usually these are well characterized because there have been a lot of chemists working on these for a long time now, and now they've done a lot of work around this. We also have things called complex reactions. These reactions consist of two or more elementary steps combined. And we can combine those steps because of Hess's law, remember. So we can have 2 steps, we can have 10 steps, we can have 100 steps, okay? And this is so we can get very complex very quickly. And this is something that is not fully characterized, of course. There's infinite number of reactions that can happen, okay? And a reaction mechanism is said to be the complete sequence of elementary steps that, when combined, come together to make a complex reaction. The example I like to go into is actually the lysis of ozone, or lysis meaning the cutting of ozone to form oxygen gas. And this reaction is catalyzed by chlorine gas. Okay. And this is part of why CFCs were so dangerous when they were used as refrigerants. Okay. So we've studied this reaction and we know the following, right? These three elementary reactions. I know that chlorine will combine with ozone to form an oxygen molecule and a chlorine monoxide molecule. I also know that ozone will, when heated or given energy, will spontaneously break down into oxygen plus a free oxygen atom. And then finally, I also know that if I take my chlorine monoxide and I combine that with my free oxygen, I will form a chlorine atom and I will form my oxygen. So if I consider adding these things together, right? Remember when we did Hess's law, if I consider the everything in the products versus the reactants, well, in my first step, I am producing a ClO, and I see that ClO is then going to be used up in step 3, so I can cross that off. I also see that I start with chlorine as a reactant and I end with it as a product. So that is going to cancel out, and that is why chlorine is considered a catalyst, because it's there to start, it's there to be at the end. It is not used up, and so it's free to continue the reaction. I also notice now that I have even further, I have my single oxygen atom here as a product, and I have it over here as a reactant. So what am I left with in terms of overall reaction? Well, I have an ozone, and then I have a second ozone. So there's 2 ozones. I have an oxygen here and here and here. So 3 oxygens. So 2 ozones goes to 3 oxygens. So that's my overall reaction. Okay, and again, this is hopefully a review of Hess's law without any consideration of enthalpy. We don't have enthalpy in this, but it is essentially going to be a Hess's law problem, right? Now, this is cool because we have 3 steps happening. Well, if we consider our reaction here, right, it says in a complex reaction, the overall rate of reaction is actually most impacted by the slowest step. So if I look at this reaction, Likely we're going to talk about this catalyzed reaction, but if I look at it uncatalyzed version of this, if I look at my reaction coordinate, right, this is going to be my slowest step because it would be a one-step reaction, and this is something that takes quite a bit of energy, right, to get up to here. Now, that's my first that's uncatalyzed. Now, if I consider the catalyzed reaction where I have, back-to-back reactions, well, I see I have one and then two activation energies. Well, they're not created equally, right? These are different activation energies. And what I can see quickly is that my second activation energy is slightly higher than my first activation energy. So that is going to be what's called the rate limiting step. It is the hardest hill to get over. It takes the most energy. And so it will limit our reaction. Okay. And so I've defined that below, right, as the rate limiting step as in the complex is that which is the slowest. And it's what limits our reaction. So here is another example. And if I see that I've got 1, 2, 3 separate reactions happening here, well, it doesn't take too much work to find that this tallest peak, that would be the hardest hill to get over. So this would be said to be my rate limiting step, the reaction that, or sorry, the step that has the highest activation energy. All right, guys, that's all I have for this video. Thank you for listening, and I'll see you in the next one.